Okay, so we're continuing our discussion on exponential functions. And so far we've talked about just the basics of what an exponential function is and the characteristics or the properties that are associated with the most basic simple type of exponential function. Now, the good news is, as far as our class is concerned anyway, when we try to apply exponential functions and we work with them in an application setting, aka story problems, it's only the basic type of exponential functions that we're going to work with. So the types of things that you've seen so far in the first two videos, this video and the next one also is just going to be a continuation of those same basic concepts. And some of that carryover is going to help you as you approach these problems. So in this video, we're going to focus specifically on how to apply the concepts of an exponential function in a scenario where growth is occurring. Okay, and then in the next video, we'll talk about how to apply these concepts in a scenario where decay is occurring. So with that said, let's take a look at our learning objectives and we'll get started. There's only two learning objectives for this video. The first one is to know the basic, the parts of a basic, there we go, the parts of a basic growth equation. So recognizing what the three parts are, what they do, and how they work, that will help us to solve problems. And then that's our second learning objective, actually be able to solve a problem that involves exponential growth. So with this said, let's get started. So first of all, realize we're only talking about growth in this video. The next video we'll talk about decay. So everything that we're doing in this is focused solely on scenarios where there is growth. And remember, first of all, if we look at a graph, what we're expecting to see with growth is that we're going to have a function that starts down here close to the x-axis, asymptotic over there, and it's going to turn and go up, and it's going to very quickly grow once we're past the y-axis. Okay, so that's the type of equation that we're working with, or type of function that we're working with. And we know from the first two videos that the sorts of equations that we're working with will tend to look like something, some sort of number, multiplied by this exponential thing. So there'll be this thing with an exponent. And the thing that has the exponent, we call that a base, which is, of course, also going to be a number, right? So these are just two different numbers. But one of the numbers does not have an exponent, and one of the numbers does, okay? So the way this typically looks, if we were to start putting in some variables, we would say the general form for an exponential function would look like a being just any number, a is just any number, times b, a number that represents the base, raised to the power, and we know because it's exponential, the exponent, that's where the variable is going to be located. Okay, so if I wanted a very specific example, I might have, maybe a is the number, I don't know, 62, just making up a number there. Maybe b is the number 1.05. Again, I'm just making up a number. And then my exponent would be my variable, in this case, x. Okay, so these are the types of things that we're looking at. And remember, because we're talking about growth, there are some things that we know about this. So first of all, because we're talking about growth, we know that whatever the exponent is, right, whether it's x or some other variable, first of all, it's going to be the variable. And second of all, because we're dealing with growth, we expect that the variable will not have a negative sign. It will not be an opposite sign in the exponent. So I'm going to write that the variable will be positive. The exponent will be a variable that is positive. But I do want to clarify, make sure that we're clear on this. When I say that the variable is positive, this does not mean that the number I'm plugging into the variable has to be positive. Because remember, even though it's growth, I'm allowed to plug in negative values for x over here, right? This is still part of my domain. I still have a point where the x value is a negative number. That's still part of my domain. So I am allowed to plug in negative numbers for x. So the exponent after I substitute could very well be negative. But the variable does not have a minus sign. That's what I'm trying to express here. And perhaps I could have worded this better. But I'm trying to express the fact that the variable does not have a minus sign or a negative sign or an opposite sign, whatever you want to call it. Okay, so that's the first thing that we're going to expect because of the fact it's growth. The second thing that we can expect because of the fact that it's growth is that the base we talked about in the previous video is going to be a number that's greater than 1. Okay, so in the last video we talked about if the base is bigger than 1 and the exponent is positive, then that is what causes growth to occur. I did mention in the last video that there is one other scenario that would also cause growth to occur, but it's a form of writing this that mathematicians typically stay away from. So as we do the problems in this particular homework set, or the homework that's associated with this video, these are what you will always see. You will always see a base bigger than 1, and if it's not bigger than 1, then that's a sign that you've made a mistake. And you will always see that the variable is positive. Okay, you might plug in a number that's negative, but the variable itself will not be negative. Okay, now all that leaves then is to talk about the number that's out in front. Okay, the number that's out in front, this a value. Okay, this a value, the number that's out in front. All right, so let's talk a little bit about that real quick. First of all, I'm going to ask you, I'm going to grab a piece of scrap paper real quick, and I'm going to play with this function just a little on a piece of scrap paper. So if you want to, you could jot this in the margin of your paper. If you've got room down at the bottom underneath where we wrote that equation, you could, do what I'm doing there. But this is something that I just want to go through a little mental exercise, a little discussion. And so you could perhaps, if you wanted, just set down your pencil for a second and just watch and listen and follow along with me. Okay, so we know that because our domain is all real numbers, the graph is going to go forever to the left, the graph is going to go forever to the right, which means somewhere, sooner or later, the graph has to cross the y-axis, right? The only way I can go from forever on the negative side and end up at forever on the positive side is sooner or later I have to go through where x equals 0. I have to go through the y-axis. Sooner or later that has to happen. Okay, so that tells me there has to be a y-intercept. And we know from previous discussions in our class, if we're going to find a y-intercept, that the way that we do that is we plug in 0 for x. Okay, so I want to think about what's going to happen if we do a y-intercept. So I'm going to evaluate f of 0, right? Plug in 0 for x. And I'm going to get this sort of an expression. Okay, now think about what happens. Because this is growth, this number right here is always going to be a number greater than 1. Okay, and if we're trying to find the y-intercept, this number is always going to be a 0. So if you think back to our properties of exponents, if I'm taking a number greater than 1 and I'm raising it to the 0 power, what is that whole thing going to become? Always, every single time. Well, everything to the 0 power always equals 1. So this whole entire expression, this whole entire exponential expression is simply going to simplify to be a 1. And so I end up with 1 times 62. And of course, anything times 1 will always equal itself. And so what I end up with is that when I'm trying to find the y-intercept just simply ends up being the number that's in front of the parentheses. Okay, and that's always going to happen because I always plug in 0 to find the y-intercept, and anything raised to the 0 power always equals 1, and anything times 1 always equals itself. So I'm always just going to end up with that number. Okay, so going back to our general form, we said we're going to call that number a. And so we can make two statements about this number that's in that slot that we're calling A. The first thing we can say is that A is always going to be our y-intercept. At least it will be here at the beginning when we're working with basic functions. And that's the type of function that we're working with right now, a basic function, a basic exponential function. We can, in our next half of our exponential function unit, we can manipulate this equation so that it's more advanced, more complicated, there's more stuff going on. And then this might not always be true. But as long as I have something that's simple and basic like this, then that will be a true statement. A will be called the y-intercept. Okay, now, with that said, I want to go back to this for a second. And again, you don't necessarily need to write down what I'm about to do, but I want to have this in front of us as we discuss this, okay? So a little bit of a background. The reason why we call it growth, right? If you think about the implication of growth, if I got a puppy and somebody comes and asks me how my puppy's doing, and I say, oh, it's growing, right? What does that mean? Well, that means if I take the size of my puppy today and I compare it to the size that my puppy was when I first got it, my puppy has gotten bigger, right? So the very fact that there is growth implies that as time goes by, something got bigger, okay? In our case, as we talk with functions, the y value is what gets bigger. Okay, now why do I say that? Am I trying to suggest that we're always talking about as time goes by with exponential functions? The answer is no. We're not always talking about exponential functions dealing exclusively with time. But many, many of our exponential functions will deal with time, and that's what this variable here will represent. Frequently, what we'll find is that the x value represents time. Now, if that's not always true, why do I even bring it up? The reason I bring it up is because it informs our vocabulary. In other words, this idea is the idea that explains why we name things the way we name it. So why do we call it a growth function? Because of this idea is what the function is describing. Okay. Now here's the next idea that connects to this. If I'm plugging in 0 for x, then what I'm suggesting is that the time is equal to 0. So what would that mean? Let's think about my puppy for a second. If I were to come up with an equation that describes how fast my puppy grows, and I wanted to say that time was equal to 0, well, what that would refer to is that would refer to when my puppy was born, or maybe when I got the puppy or something. But it refers to some beginning point in my puppy's life, some beginning measurement that I took. And then once I measured my puppy on that day, I started a stopwatch. And then as time went by, I can calculate how big I expect my puppy to be. Okay, so that means the number that we have right here, the number that is our y-intercept, what that number represents, in the case of my dog, that number represents how big my puppy was initially, at the very beginning. When I started the stopwatch, how big was the puppy initially? Okay, now that is the actual vocabulary that we use. Even though not every function deals with time and puppies, that's obviously not the case. Not every function will deal with time and puppies, but the vocabulary that we use is that same vocabulary. We call this, usually we don't call it the y-intercept. Sometimes we will, because when you graph it, it is the y-intercept. But more commonly, we tend to call A is usually called the, and I'm going to switch colors just to sort of highlight this a little bit. It's usually called the initial value. Initial value. The initial value. A is usually called the initial value. And the reason we call it that is because if this was a problem that dealt with time, then A would be the measurement we had when the stopwatch got started. Initially, at the beginning of our experiment, at the beginning of our measurements, whatever A was, that was the measurement that we took back then. Okay, so this is the basic parts of our exponential function, which is learning objective number 1. Know the basic parts. So this number, whatever number is out in front, that's our initial value. B is the base. It's going to be a number that's bigger than 1. Now, I didn't mention here, but as a side note, mathematically speaking, B is somehow going to be connected to a growth rate. So you're going to see in the example we're going to look at right now that there will be a rate in the problem that explains how fast things are changing, and B will be related to that number. And you'll see that in our example that we'll do in just a second. And then last but not least, X will be the exponent. It'll not have a negative sign in front of the variable, and it's going to represent something going, some ongoing process. So maybe it's time going by. In fact, I think in all of my examples today, both in the notes that we're about to do and in the homework problems, I think it represents time in all of them, if I'm not mistaken, but it doesn't have to represent time. Okay, so with all of that said, let's move on to learning objective number 2. Let's actually do a problem. So I've got a problem right here. I'm going to put it up on the screen for you to see. The first thing you should do is pause the video and copy this problem in your notes. Okay, so do that now. Pause the video and get that copy down. All right, so hopefully you've copied this. If you remember our 5 steps from last semester for solving problems, we said the first thing you want to do is understand the problem and not worry about the numbers or the formulas. Those little details cloud the issue. We want to just have an intuitive understanding of the problem. If this was a story that you were reading in English class, if this was the latest adventures of Harry Potter, what sort of plot twist do these sentences describe? Okay, so how would we talk about what's happening in this problem? Well, what I would say here is that I have an investor, a person, right? An investor is just a person who is trying to take their money and earn more money from it. So I've got a person. Deposit means they put the money into the bank or whatever their savings vehicle is. Let's just say for the ease of discussion, their savings vehicle is just a regular savings account. Let's just say they're putting it in their savings account. So I've got a person who puts money into their savings account, and that money gets a return. It earns interest, okay? So if you're not familiar with how banks work and things like that, if you give the bank some money, you put it in the savings account, the bank pays you for letting you use their money. Because you've put it in the account, you're letting them use your money, they pay you for that, okay? So that is called interest. So we give the bank some money, the bank gives us some interest, now we're making money. The next sentence says the investment is allowed to compound. Now what compounding means, this might be a word you don't know, depending on if you had econ or a financial math class or anything like that. What compounding means is that as we earn interest, that interest gets reinvested back into the savings account. So when they give me my interest on this, I don't take that interest and go and buy myself a cheeseburger or something with it. I put that savings or that interest back into the savings account. So now I don't have $2,000 anymore. Now I have $2,000 plus however much interest I had. So let's just say for easy numbers, now I've got $2,010, okay? Then the next time I earn interest, I'm earning interest on 2010 instead of just 2000. So I'm earning interest on my interest. And what happens is I end up making money much faster that way. Compounding interest, it turns out, will always end up being exponential growth. Okay, so this person invests some money into their savings account. They get interest on it, and they reinvest the interest so that their interest will also earn interest. This causes exponential growth, and that exponential growth is going to go on for a while. The question is, how much money will it be worth after that time goes by? Okay, so that's a basic understanding of the story. Now, the next thing we want to do is organize the data they gave us. So if you think about our 3 steps that we've learned, we want to organize data next. So one piece of information they gave us was this $2,000. Another piece of information they gave us was this 3%. And the last piece of information they gave us was this 15 years. Okay, so what I want to do is I want to think about what do those pieces of information tell me? Well, the $2,000, that's how much money we started with. I'm just going to say money at the beginning. But how much we started with, okay? If you think about to what we just got done talking about here, if this is the money we started with, what does that sound an awful lot like? Doesn't that sound like an initial value, right? The money we started with. So this is our initial value. So in just a minute, when we start making an equation, this is going to end up going into our value for A. Okay, 3%. 3%, that's describing how it's changing, the amount of growth that we're getting, how much money they're giving us every time, okay? So this describes the rate of change. Describes a rate of change. Okay, that's what that's describing. How fast is the money that I have changing? Now, I do perhaps, again, perhaps this is a poor choice of words. This is not the same as a slope, right? Because this is exponential growth. It's not linear growth. This is not the same as a slope. But and we usually talk about rate of change as describing slope. So maybe this is a bad choice of words, but it's definitely describing some kind of change. Okay, so maybe I don't say rate of change. Maybe I just say change. Is that okay? All right, and then last but not least, 15, well, that's how much time goes by, obviously. All right, now, as we organize data, there's one more piece of data that we have, but I haven't written down. And the reason I haven't written it down yet is because the last piece of data is not actually in the story. It's in our notes. The last piece of data we have is that exponential growth equations are always going to look like this. So what I can do is say, all right, I know my equation has to look like this. Can I figure out where to put the different bits and pieces? So the first bit, like we said, the 2000 is the initial value. And we know that A represents the initial value. So I think this is going to become a 2000. Okay. Now B is a little bit tricky. I said that B is going to B is going to have something to do with the way things are changing. So obviously that means it's going to have something to do with the 3%. But let's think about this for a second before you just jump and put in a 3 right here, because that would not be the right thing to do. We don't want to just put a 3 in for B. But I need to put something in that's related to that 3. So what do I put in? So first of all, how do I know that I don't just put in a 3? Well, here's how I know. As soon as I see percent, right? Percent means literally, it means per 100. And the word per literally means divide. So this literally means 3 divided by 100. Well, 3 divided by 100, that is 0.03, right? We've got to move the decimal 2 places. And I know that that cannot be the thing that I put in for B, because if this is a growth problem, B has to be bigger than 1. And this is not bigger than 1. So it turns out, and this is another one of those spots in our class where we could go through the math and I could prove this to you, but it's a little bit beyond the scope of our class. It turns out that the number that's going to go right here will always end up being a 1 plus this percentage, a 1 plus this percentage. Okay, so that might be something to make a note. Always 1 plus the percentage. Okay, so in this case, it's going to be 1 plus 0.3. So 1 plus 0.03, right? Because we moved the decimal 2 spots. So that means it's going to be a 1.03. Okay, so this is my function. That's my function. So all I need to do to figure out how much money I have, that's what f of x is going to be, how much money I have. Sorry, I can't spell how much money I have. There. Doesn't matter if I can't spell it if you can't see it. I'm sorry about that. How much money I have is what f of x is. I can figure out how much money I have by just simply plugging in a 15 for x and then simplifying that expression. Okay, so remember, order of operations, I'm going to have to do the 1.03 to the 15th power first. So on my calculator, 1.03 to the 15th power. Remember, to get that crazy exponent, I'm using the caret button. Okay, 1.03 to the 15th power. And now I'm going to multiply that by the 2,000. So that thing times 2,000 times 2,000. There we go. All right, now let's talk just real quick about what sort of answer makes sense. So what I'm saying is the money that I have is now equal to 3115.934833 is what my calculator says. All right, does that answer make sense? Well, the first thing I should recognize is it doesn't make sense because when we're talking about money, we never have decimals that look like this, right? We can only have a penny. We can't have less than a penny. So this stuff is not part of my answer for sure. So I might say that I currently have this much money, whoops, 9.3, in my account. I might say that. And that would be a good, fine, correct answer. I might choose to round that off and say, that's about $3,016. And that would be a fine answer, okay? I would say in this case, probably most people would round it off even more than that and say, I've got about 3,100 bucks, okay? So remember, if you're filling this answer in on the SAT, in the gridded response, there's only 4 gridded spots. You can only have 4 digits for your answer. So for the SAT, this is what I would need to put on the SAT right there, okay? But for the purposes of casually talking with your friends about how much money you have, obviously that's a fine answer. And if you're somebody who's actually trying to calculate to the penny, how much money, what can I expect, then that's the kind of answer that you're going to want. Okay, so that takes care of learning objective number 2, making sure that you understand how to find information within a story problem and then use that information along with our exponential growth equation to find a solution to whatever problem that they ask. Okay, so hopefully that helps you with this. That's the end of this particular video. In the next video, we'll go through this same process with the decay problem. But for now, we're all set. So thanks for watching and have a good one.